Hello, this is Jette Wagen, and this is the third video in a series of videos in which I will be introducing QGIS 3.4 long-term stable release. In this video I will be dealing with a couple of subjects. First of all, I want to demonstrate how you can use Access Microsoft Access data in QGIS. Furthermore, I want to deal with joining data between layers. I then also want to show how to make a simple distribution map. And I want to finish with some basic data conversions and analysis in QGIS. Okay, so to start with the first subject, dealing with databases. Now, the QGIS has a whole range of tools for dealing with databases, and I will showcase a little bit the different possibilities, but I will mainly be focusing on how to work with a Microsoft Access database, because that is the least straightforward database type to work with in QGIS. But on the other hand, in archaeology, at least in the Dutch context, but also I think in the international sector, Microsoft Access databases are often used, if not still the most common database type, for several reasons. Reasons that have to do with the portability of Microsoft Access, the fact that it's almost standard, available on a lot of computers in academia, the fact that it has a very good system of working with forms and views, and I think it's in any case the database that is the easiest accessible for many archaeology branches. So I think it's still very important to show how to deal with that type of database. However, before going to Microsoft Access databases, I will give you a quick taste of the way QGIS deals with databases. And for this we will start with this option in the menu of QGIS, which is the Database Manager. Now, if we look at the Database Manager, you can see that it allows us to access various types of databases. I won't go through all of them, but maybe a name that may ring a bell is, for example, PostGIS, which is a spatial extension of PostgreSQL, and which is of course a multi-user server-based database that is often used. And you can directly import data if you provide QGIS with the right location of the data and all the registration information that you need to have. On the other hand, it also works with SpatialLite. Maybe SpatialLite rings a bell. It is the spatial version of SQLite, which is maybe a bit more known, and you can also directly import data from SpatialLite into QGIS. And the advantage of SpatialLite is that it is like Microsoft Access, a portable database format. So it's actually a database that you can copy from one location to another, place on a USB stick, send over as an email attachment to someone else, and you can directly open it, which is of course a bit different than how something like PostgreSQL works. Now, it's also very easy to create, for example, a SpatialLite database using QGIS. You can see here in the browser panel that these database packages are also listed in the sources of possible data. And if you would, for example, select SpatialLite, hit the right mouse button and click on Create Database, you are enabled to create a SpatialLite database. So let's go to the right location on our drive, and we can make an example database. And now we have a SpatialLite database that we can directly access from this menu or the browser panel. So we can also access this now through our database manager, in which it is immediately made available, and we can create a table, for example. So now we can just start creating tables, adding fields, and having a database directly available in QGIS to enter data, to digitize in, as an alternative, for example, to digitizing into a shapefile. Okay, so that was very short on how to access different types of databases through QGIS. I will now turn to connecting to a Microsoft Access database. And in order to do that, we have to start with Windows. Because what we need to do is we have to configure the Open Database Protocol to connect with a database located on our hard drive, which is a protocol that QGIS on its turn can then use to access that specific database. So we have to first configure in Windows and then make sure we create and establish this connection from QGIS to the Open Database Protocol. Okay, so the fastest way to access this this data protocol, we go to Start, or rather Search, and we enter Open Database Connectivity, and we select the correct bits version for our computer. Okay, here we can select Add, and we will be able to add a driver for a data source. And you can see that we can now add various Microsoft products here. We want to add a Microsoft Access database, so a .mdb or .accdb, and we select the driver for that, and we click on Finish. Now we can give it a name, and the name here is important to remember because this is the name we will have to also configure in QGIS, so he looks for the right object. And of course we have to select the database that this name refers to. So select, and we have to go to the drive and to the folder in which we store our database. And there it is. So I now just hit OK again, and there it is, Nijmegen. And I hit OK again. Okay, and then from within QGIS we can now simply go to Add Vector Layer. Here we can set a source type, so instead of file we will set database. The type indeed has to be ODBC, and we will add a new connection. So we click on New. Here again we set the type to ODBC. We can give it a name. Now let's say Nijmegen database. I need to set the host, which will be the local host, because we are referring to the database protocol on this computer, and we want the database name. So this is the actual name that we just configured in the Open Database Connection Administration window in Windows. Okay, the port is fine. We do not want to set any authentication, and we test the connection, which is successful. So we hit OK, and we hit Add. Okay. And of course we didn't need a password because I didn't set any authentication. Okay, so now we have direct access to all layers in this database, and we can select one or multiple layers now to directly add to our GIS project. For this demonstration, I created a table, which here has been attributed layer ID 1, which is called Trench 31 put 31 sporen, so Trench 31 features, and I will add only this table. So I hit OK, and I can close this window. Okay, so as you may notice, indeed, there has been added now a table. So we have also now suddenly a new icon. So we don't have any vector or raster indication, but you can see here indeed the sign of a table and ODBC with Nijmegen put 31 sporen. So what now happened is that this data has been added as a table. So this data does not have any spatial definitions or geometry in it, so there's nothing to visualize. So there's also nothing to turn off or on, because this is a simple table with data in it. Now we can of course look at it by opening the attribute table, and this is directly the data as it is in the database. Now there's one important thing to say about this data. What we now have is data which is directly imported from the Microsoft Access database, and it's also still linked. So what I can't do at this moment is now turn on an editing mode, because the connection through the protocol does not allow that we use QGIS to edit information directly in the Microsoft Access database. So this is a bit different than if you would work with SpatialLite database. You could change immediately all the data and it would be updated with the data source. When we work with a Microsoft Access database, this is not the case. Okay, so what I now want to do is I want to connect the data from this table to my shapefile containing the spatial definitions of the features in Trench 31. I will make it a little bit easy now, so I will make a subselection of my my features file to only contain all the features from Trench 31. So in order to do this, I will start a by now familiar procedure. So I will open the select by expression in the attribute table, go to fields and values, select trench equals 31, and I select features. Now I will go to show only selected features to see if my query works, and it did. So now I only have my selected features, and I will just zoom to selection to have this confirmed, and I will turn off all the other data so it's a little bit easier to see, and this is indeed Trench 31. And then I will save this to a different file. So I will go for the right click on the layer, exports, and save selected features as. Now I will just save this with the simple name of Trench underscore 31. Save. Okay, and there it is. Okay, so in order to connect these two data files, I need to make sure that there is a corresponding and unique ID in both of them. Now for the shapefile, this would be the data in this field, which is the feature number. So we have stored them 1 to 9, 999, and here 3 entries into the 5000. And I will look into the attribute table of my imported Access database file. and I can see that that this contains the same numbers. So we see here that we have 1 to 9, 999, and then some numbers in the 5,000. So there are a bit more numbers in the 5,000s here than are in my shapefile, but at this moment I do not really care about that. This may have something to do with negative archaeological features, which is something that only makes sense if you know archaeological stratigraphy, but in any case there may be also just errors. I don't know. This is not my data file, but as I said, at this moment it's not really important. What is important though is that you need to connect this data, and then the IDs connecting the data need to be exactly the same and also of the same data type. And here you see maybe already a potential problem, in the sense that in the attribute table of the shapefile, we see here the numbers lined out to the right of the field, which means that this is a numeric data type. And we could also find this out in another way if we want to know specifically, to go to the properties and look for the fields in this this table. And here we could see that indeed we have here a long integer 64 field of 10 characters length, or numbers length I should say. And so this is a numeric field. Now if we look closely at the table, I have a couple of them open, I see. If we look closely to the table from the database, we can see that we have here a different configuration, because we see here that they are outlined to the left, which means that they are actually text, stored as text entries, and that there are leading zeros. So we have leading zeros here, and of course it's only possible if you use text, because if you would enter 0001 in a numeric field, the 3 zeros would simply be ignored. So this data in this shape will not connect properly. Okay, so in order to make it connect properly, we need to change a field or add a field in either one of these tables to change this situation. And in this case, I will be going for a change in the shapefile. Now, why do I choose for a change in the shapefile? I may want to repeat this process, and if I repeat the process, which I mean I import data from the Microsoft Access database, I will again get my feature numbers with these leading zeros. So if I do not want to change every time I import this Microsoft database table, which may be updated because the data processing from the finds administration is still going on, for example, it is better if I make sure that the shapefile is changed, because that is a rather static file, at least in terms of numbering, and I only have to make the change once. So that's a very simple reason to choose for changing the shapefile. So let's do that. Now again, I've been going through this before, but we can enter an editing session for this this attribute table connected to the shapefile. I can add a new field, but if I use the open field, the field calculator, I can also directly create a new field. So let's do that. So I have now here create new field. I want that field to have a name. So I will say that this is my connection field. Okay, so there's a maximum number of characters here, so I'll just leave it as sporen_con. I do not want a number field, I want a text field, because I need to add the leading zeros here to be able to link to the file. and then I will leave the rest as it is, and I will write an expression that will actually give me um, the numbers from my column sporen. So I want the numbers from the column, which is actually called number, which refers to the feature number. But I want to make sure that I add these leading zeros. Now, of course, there is a function that does that, and here Google is, of course, your best friend. And I need to set this function properly so zeros are being added to a maximum of 4 numbers in this in this entry. Okay, so the expression that we need here is left padding. Open and close. I then need to add the field name in which that I want to use the data from. I then have to set how many characters do I want to fill up the information from that field, which will be transported to a new field, of course. And then I need to add what character do I want there, and because this is a text field, we're now talking about numbers as characters. And I will say that I want a 0 added for every empty spot when the information from the field number is being left padded up to 4 characters. So this is what I want, and I will hit OK. You can also see an output preview from a random record in the attribute table, so you can see here directly that this is indeed going to give us the result that we want. And if I hit OK, then we have our fields. So we have here sporen underscore con, and we have our left padded leading 0 fields that are now actually exactly similar as the fields in the database table. And so I can now finally establish this link. Okay, so now in order to establish this link, we go to the properties of the layer we want to link with the database table. So I go to Trench 31, right-click Properties. I have here a tab which is called Joins, which is the name in GIS for connecting data. I will then click on the plus sign, add a new join. Here I can select every data that actually, every layer that has actually data that we can join in this way. This is a vector join. So I'm only presented vector layers and database layers. Now I will of course connect the ODBC database table. We have to set a join field. Now it's going to be spore, so the feature number. Then we have a target field, which is going to be from the shapefile itself. So that's going to be the field we just created. And we want to set which fields we join. Now, and in this case, I am specifically interested in the feature interpretation, and maybe I want to know a bit more whether there have been any specific comments about the fields. And I think a begin date, end date, begin period, and end period may be interesting to add to the connected fields. So I hit OK. Now I have here my joint database table. I will click OK, and if everything went as it should, I will now have my data from the Microsoft Access database imported table connected to my shapefiles attribute table, and indeed we have it. So we have here our data from the attribute table of the shapefile up to here, and then from that point onwards you can see here the ODBC connected records. Now we have here the interpretation, we have here the dates and periods, and we have here the comments which are none. but we have our connected data, and this we can again demonstrate this by identifying one of the features in our layer, and then you can see that indeed we have now all the information directly connected. This is apparently a ditch with a very specific date in the Bronze Age. So yeah, this is how you establish such a connection between layers, and in this case, specifically with an imported Microsoft Access database table. Okay, so now that I showed you how to connect to a Microsoft Access database, I want to finish with that with this session on external databases. And in the second part of the screencast, I wanna start with showing yet again how you can import data from an external data portal. And in this case, I will select the data portal of the National Heritage Agency, the Rijksdienst voor Cultureel Erfgoed, that actually has a database of all archaeological monuments, excavations, and events. And this is, of course, for the Dutch sector very relevant to be able to do this, but there are many of these types of portals in other countries as well, of course, so this is also a demonstration of how to do it, and getting vector data from external source. Now, in order to access this data from the National Heritage Agency, which is called, you have to access a system that's called ARCHIS, and I will go to that system by just entering ARCHIS 3, because it's version 3. And there I go to indeed the first link, so ARCHIS Rijksdienst voor Cultureel Erfgoed inloggen. And here I get to the login page, where you can access various services of the of ARCHIS 3. Now, there are many different things that you can do, and it also depends on the type of access that you have to this data, because archaeological companies will have different types of access than, for example, just an interested citizen. I will use my simple search and find account to get into the system and get some data that may actually be relevant for the data we are examining of the excavations in Nijmegen. So I will go to Open Zoeken en Vinden, search and find. Now I have a registration already, which you can get by contacting the National Heritage Agency, and I'll hit OK. And here we get into the system with which we can actually look for well, we can search through all the archaeological information that's stored here. In order to make this a bit easier, I'll go to the map, and I will zoom to the area we are currently working in. Which must be more or less here. Okay, so let's suppose I want all the archaeological information stored in this online system that surrounds the field where the excavations took place. So I can use here a select tool, and in fact this is an online GIS for WebGIS. So it performs similar to what we see in QGIS. We select these features. These are vector features, so if we take the selection tool, intersect is being now selected. If I then go to this tab over here, archaeological events, I can see that indeed I have a set of results that corresponds to the selected features on the map, and this is of course analogous to what we've seen so far in QGIS. Map elements are directly connected to the database, and the selection in one is the selection in the other. Now I want to use these 39 results because it's interesting, possibly interesting archaeological information that I would want to be able to compare with my excavation data. So I will hit for that download and then choose for GeoJSON and download the data. I will save the file. I will retrieve it from the download section, and then we can go back to QGIS after I store it, of course, in the dataset that we have already working with. So I will save it here and go back to QGIS. Okay, so in QGIS then I can enter this data by adding a vector layer. We'll set it back to file, select the dataset, so I have to hit that button. And then there's another feature in QGIS which is quite useful. You can, if you look for a file, look for every file. So here you see all files with the asterisk. But if you want to only look for specific files, and it can of course be very useful if you have folders with a very large number of files which are not all of the same type, then you can set here a type and it will only show you the file types for which you are filtering now. So if I select here GeoJSON, we can actually see here the GeoJSON file that we entered into this folder, that we copied into this folder. And of course, if you're not finding a file of which you are sure that should be here, it is very wise to double check if you are not only set to recognize a specific file type. So now I will just open this, add, and then close. And now we see that we have here RCE all added to our project. Now we are very zoomed in on our trench 31, so I will right click, zoom to layer, zoom out a bit in order to see the rest of or in order to see the information at all. I will turn on the complete excavation, and I will turn on the aerial photograph for a bit more contextualization. And if we now zoom in on the terrain, we can see that there are indeed some archaeological events connected to the terrain, and we can now of course also access the information that we downloaded from the web portal to see what this amounts to. And here we can see that this is indeed a registration of an archaeological find, and it's something, it's prehistorical pottery that has been found there, and it may very well be that the identification or the sporadic finds reported by people who came across these finds were actually the reason why this sampling layout of trial trenches was actually dug here to see if there was maybe an important prehistoric settlement to excavate. So there it is, the online ARCHIS data directly into your QGIS for you to analyze in connection with the excavation results. Okay, now in the last phase of this video, I want to show how you can do some very basic analysis in QGIS by using the geoprocessing tools. Now, in order to do that, I'm going to turn to a bit of an artificial scenario, because I do not really have very interesting data to do basic analysis, use geoprocessing tools. So we're going to work with an artificial scenario in which we are going to assume that these individual finds that we added to the projects from the file earlier, that we are interested to see whether there is some clustering in them. So of course these finds come from trenches, so in any case there is a spatial patterning in them through the constraints of the trenches. But we'll ignore that for now. We'll just take these as finds that have been attested in this area, all related to the prehistoric period, and we want to find out whether there is some kind of clustering that may be of some significance to, let's say, the intensity of human activity in a specific subpart of this area. Now, and then again, to do spatial clustering analysis, there are, of course, good tools for that. QGIS is also able to perform spatial statistical analysis, but in this case, we will go for very simple visualization analysis. Now, what I want to do in order to perform this analysis, I'm interested in potential, in what happens if I create buffers around these fields, around these finds, so we can see where the buffers give us a visual idea of finds that are closer or less close to each other, and maybe form some kind of clusters. Okay, now in order to do this, I will go to the vector menu option, select Geoprocessing tools, and then I will select buffer. Now what this buffer is going to do, it's going to place an imaginary rod at the center of this find. I can set the distance of this rod, and let's say I want it to be 40 meters long, and it will then draw a perfect circle around the point. Now of course I need to select the correct layer, so I want this to do this with the finds that I added earlier. And I think the most important thing here to mention is that I want to create a temporary layer. Now this is very convenient that QGIS offers the option of creating a temporary layer. So instead of saving the result of this analysis directly to your hard disk, it just creates a file in the RAM of your computer, and it will add it to the layers panel, and you are then able to inspect the results. And if the results are not what you want them to be, you can just remove the temporary layer from your layers panel, but you are not going to have to remove anything from your hard disk. So that's very convenient that you can, let's say, work a little bit quicker without creating a whole mess of files on your hard disk that you may forget to delete or whatever. So we'll do that. And as I said it to 40 meters, and let's see what we have. Close. And indeed we can see that if this 40 meters would be a meaningful distance somehow, it is indeed creating find buffers that are actually overlapping, and there are also some distances between various overlapping concentrations of overlapping buffers. Okay, now I want to visualize this a little bit better. So what I want to do actually is to create an outline of these overlapping polygons, so that they are forming one polygon per imaginary cluster. And then we can also attribute different colors to these different clusters. Now in order to do this, I need to use a geoprocessing option which is called dissolve. And dissolve means that we are actually going to merge all these features. And for those who paid attention, you could have seen that in the geoprocessing buffer tools, there was already the option to dissolve the results. But there's also, of course, the geoprocess solve separately, and we are going to use that now. Okay, so for the dissolve action, we are indeed going to take this buffered layer. So you can see here that this temporary layer has been created, and here you can see this little sign means that it is only there in your running memory and not on your hard disk. And well, we don't have to set any specific options here. You can set some fields on which you want to specifically dissolve, but we don't want that everything to dissolve. And we of course want to create a temporary layer and open output file after running the algorithm. Okay, so if we then look at the result, we can now see that we indeed created different polygons. But also what you may immediately notice is that if I select one of them, they are actually all selected. Now why is this? It is because this dissolve action is actually not making any separation. It literally dissolves all the geometrical features in the layer. So it doesn't really care whether these are overlapping or intersecting features. And what it does, it creates a so-called multipart polygon. So this is now one polygon with one entry in the attribute table, which you can see here. What we would actually want, of course, is an individual polygon for each of these 5 clusters that we identified here through buffering analysis. Okay, so how do we do that? For that, we need a tool which is called, let's see, Geometry Tools, Multiparts to Singleparts. And again, the process is very simple. We select dissolved, which is the result that we created with the dissolve action. Again, we are happy with the temporary layer and we want output file. So let's run it. Let's close it. And now we can indeed see individual clusters. We have an attribute table with indeed in 5 individual records. And that's exactly what we want. Okay, so now we can throw out at least these 2 temporary layers, so we can just remove those. There you are. And what we now have, we have of course a visual hierarchy between these 5 clusters, although these 2 may be more or less of the same area. And we may now want to actually show which one is the largest, and we can do that by calculating their respective area. We can also do that by showing how many finds these buffers are actually created, and then of course the final at most the normalized value to demonstrate that with would be a density of finds in every cluster. So we can now, in 3 subsequent steps, visualize the relative densities. So first of all, we would be interested in calculating the respective areas. So for that we go to Singleparts, open the attribute table, and we want to go here for the field calculator, create a new field, and we want to go for the geometry. And in the geometry we want to have the area calculated. So this is a preset function that you can just select and then it will run. So let's do that. And now we have here indeed a number that indicates the area. And the area is of course expressed in square meters. So now I have the calculated area, but I also want to calculate now the number of finds that are actually within the area to be able to count or to visualize the density. Because of course we may have a small polygon, but if there are twice as many finds in the polygon, it still may be, depending on many factors of course, that there would be much more indication for and more intense human activity in the past. So let's go and do that, and there's a tool for that. We go to the vector analysis tools, count points in polygon. The polygons for which we want to count the number of finds that fall within it are single parts. Indeed, also the finds are already selected, which is good. The number of finds will be tabulated in some points, which is fine as well, and a temporary layer. So to run this, close, we will have a look at the new count layer and see if indeed in the attribute table we now have counts, and we do. Okay, we can already see that this is an interesting result, because if we sort the records from small to large based on the number of points in it, we get a different sorting than when we do that with based on area. So the second to the largest polygon here actually has 10 more finds in it. So this is going to show in the density. Okay, so let's create density. So the count of finds normalized for area. Now we can do this with a very familiar tool. We want to create a new field. We will call it density. And now we have to be a little bit careful here, because we are going, of course, if we are going to calculate the density of finds, we will calculate very small numbers, because in the end the proportion of finds to square meters is of course extreme, and there are very few finds for the number of square meters. So we have to make sure that we enable decimals, because otherwise we are not going to see much, and we'll just have zeros as densities. So the all number integer is not going to do it for us. So we are going to go for the decimal number double. Now and then the actual calculation is very simple. The number of points divided by the number of square meters. Click OK, and now we see that we have here very small scores. But for the for expressing relative proportions, this really doesn't matter, of course. So we can now close the table and make the final visualization. Okay, so we just to show, I can stop the editing session of my count. I will throw out single parts as well. And now it is also time to make this, because this is a result that we want to work with and we are happy with. So we will save this as an actual file on the hard disk. So it's save features as. Still keep my as a shape file format. I will call this polygon density. I'll save it. Now I can also throw out the temporary file count. Now I can go into the properties of the polygon, go to symbology, select a different symbol. Then of course now select, for example, graduated, because we have numeric values that we want to base visualization on. We select density and classify, and let's say we are happy with this visualization. We hit OK, and then we can indeed see that based on the density we have now two relatively small clusters, a bit bigger, but actually the largest one number of square meters, is actually not the most dense one. So yeah, as I said from the beginning, this is a very artificial example fabricated by when it comes to the archaeology, but it's just to show how you can build up your basic steps in the analysis. Of course, I only used a few options, but there is an enormous amount of analytical tools available in QGIS. So I would suggest go and find out what you can do. Now, with this final set of steps, I've come to the end of the screencast, in which I've shown how to deal with the Microsoft Access database in QGIS and given you some sneak peeks of how to work with the other types of databases. I've shown how to access an online web portal, download vector data in a GeoJSON format, and add it to your GIS. And finally, I've shown you a series of steps which are useful for basic geoprocessing actions and analysis. And so we've come to the end of this screencast. Thank you for watching and listening.